Okay, so this is a quick summary of some of the key ideas you should have learned from the Waves on a String lab. We're going to discuss how you change the key measurements of any wave, be it sound, light, water waves, earthquake waves, etc. This is common to all of them. Light is a little bit different in some small details. I'll highlight those when they become relevant. Okay, so let's start with this frequency. So frequency is not something you tested in the lab because it was something that's controlled by the source of the waves, okay? In other words, in the lab, you had that little mechanical oscillator, the piston that went up and down. Okay, so you changed that and that changed the frequency. It was not dependent on amplitude or anything like that. So frequency depends on whatever source is creating the waves. Let's say the sound you're hearing now, that's coming from my voice, from my vocal cords, right? I can go to a high or low. So I'm altering the air passing through my vocal cords to change the pitch that you're hearing. You can stop laughing now. A key equation I want you to know, the relationship, you didn't test, but we've been talking about all along, is the relationship between frequency and period. Okay, so they are interdependent on one another. I know there are other equations that have frequency in it, like V equals lambda F, but F does not depend on those other two measurements. It's just a part of that equation. Okay, another example of this with frequency is take any instrument. Take a stringed instrument like a piano. Okay, the frequency you hear in that case depends on which key you hit, which is dependent on which string you are essentially hammering or plucking if it was a guitar. Okay, so it's not how hard you hit it, it's the actual string itself and the tension too. All right, amplitude. All right, you tested this. That was pretty straightforward. It was simply dependent on how far that piston or shaft moved. It did not depend on the frequency, nor did it depend on the tension. Okay, so what is ultimately amplitude about? Well, if you were to take a string and you were to pluck it, the further you pluck it, the bigger the amplitude you give it. Okay, and if you pluck it further, that means you're doing more work. You're exerting a greater force to move it sideways over a greater distance. So ultimately, and this is key about amplitude, is it depends on the energy you put into the wave. All right, so if I start talking really loud, I've put a lot of energy into my voice, or I can whisper, not a lot of energy. So that affects the amplitude. Okay, so put over here, amplitude increases with energy. Okay, I believe this is not something that we have to worry about right now, but the energy is proportional to the square of the amplitude. Okay, and what we want you to understand is it definitely does not depend on the frequency, and it does not depend on how fast the wave is moving, the velocity. All right, let's move on to wavelength. Wavelength from the lab had the most interesting results. Okay, it depends on two things. It depends on, first and foremost, what you'll see a lot throughout this whole unit. Okay, this is one of the most important relationships in unit, is it depends on frequency, and it also depends on medium. That doesn't come up as much because usually when you're creating waves, the medium is more or less constant. When I'm speaking or any sounds are played, it's usually air that's the medium. Even if it's in any instrument, the sound you're hearing is that medium. So to change media for a wave is not common. It's not rare either, but we don't talk about it as much. So the key thing we want you to understand is in terms of frequency is you should have seen from the lab there's an inverse relationship. So as F increases, lambda decreases. Okay, so that's classic, right? Lambda is proportional to 1 over F. Right, in terms of medium, okay, medium, I'm going to come back to this idea, but I don't have a measurement for medium per se, but it is directly related to velocity. All right, so let me make that connection a little bit, but we can make the mathematical statement as velocity increases of a wave, the wavelength will also increase. And again, that's easy to forget, but it does come up and you need to be aware of that. So we can say lambda is proportional to V. In fact, if you put these two proportionalities together, you get lambda is V on top over F on the bottom, which is nothing more than our wave equation. Okay, lastly, velocity. And this is the one that's perhaps most misunderstood by students. Velocity depends only on the medium in which you're creating that wave. It does not depend on the energy. It doesn't matter how loud I speak. The speed of sound is not going faster. It doesn't matter in water if I do a cannonball or I dive in with my toes and barely create a splash. The speed at which the ripples go out is the same regardless, because it's the medium that matters. Now, in the lab, you change the medium not by changing the actual material that the string was made of, but instead you changed it on the tension. Okay, so that's when you change the tension settings, in essence, you are changing the medium. You're really changing the strength of the intermolecular forces or the restoring forces. So if you really want to get down to it, it's ultimately the strength of the restoring force that determines how quickly a wave propagates in any situation. Okay, another factor that matters that won't come up much, but I'm going to mention it here, is something called linear density. So I can take, for example, a piano. I can put 3 piano strings under the same tension. And you might think, well, then the wave through that string should be the same for all 3. But if the linear density, which means mass per unit length, for the strings are different, then the speeds will be different. So any of you who play string instrument who have worked with different linear density strings, thickness of strings, will know that you get different notes. Okay, so what we want to say then is as tension increases, okay, velocity increases. That should have been pretty clear in the lab. All right, and we want to reemphasize that it does not depend on frequency. So if you play an instrument like, let's say, a xylophone, it has multiple notes. The speed of sound coming out from every bar is the same. It doesn't matter how hard you hit it or which bar you hit. So it doesn't depend on amplitude at all as well. Okay, so I want to finish up by doing a simple little example. Maybe not so simple, but it covers a lot of, it's one example that covers a lot of ground. So let's say I have a light wave, continuous, so it's shown down here, traveling and enters a long transparent block of plastic. At the boundary, some of the light is reflected, but most is transmitted through the block. That's very common. So even if that block is glass, there will be some reflected light, about 4%, but most will go through. And then it comes out the other end. The tension, and I'm referring to this tension, it's not really a tension in there, but it's the closest it can come to with light, is less than in air. Okay, so we can ask how all of these 4 will change as a result of entering that block. So I will go through these, but you should think of these yourself. So amplitude. Will the amplitude of the wave inside the block change? Well, what does amplitude depend on? If you go up there, you see it depends on energy. So yourself, does all the energy of the light enter the block, or does all the light enter the block? The answer is no. We see up here that some of it is reflected. So amplitude slightly decreases, okay, because some of the wave reflected. All right, so we're going to draw this wave through the block in a minute once we cover all this. All right, how about frequency? Does the frequency change upon entering this? Well, we go back up to the chart. What does frequency depend on? The source. Well, where is the source? It's not the block. The source is over here somewhere. Okay, it's whatever is creating the light. Okay, so that's not changing. So frequency stays the same. I'm just going to put same because source is the same. Okay, so you're going to find that frequency rarely changes when we go from one medium to another. It never changes, okay? But it might be confusing to think it does. All right, how about the speed of a wave? All right, we go up here, speed of wave depends on the medium. Well, we are definitely entering a new medium, so we expect it to change. The question is, does it go up or go down? Well, I gave the detail that the tension is less. Okay, so we see that as tension increases, velocity increases, so we'd expect the velocity to go down, decreases. Now in reality, there is no tension for the light. There's actually something called index refraction that we learn in year 2, but I'm not going to go down that road right now. Okay, so we can say speed of the wave decreases because medium. You won't have to know about that kind of tension for light and any problems. You'll have to understand it for tension and strings. High tension means higher speed. Medium I know this is not the best way of putting it, but I don't want to get bogged down in words, so I'll just say medium decreases. All right, lastly, wavelength. Okay, so wavelength we saw depended on two things. It depends on frequency and it depends on medium. Okay, the frequency stayed the same, but the medium changed. In fact, the medium we just kind of said decreased, okay, or the speed went down. So if the speed goes down, then we expect the wavelength to go down as well. Okay, because F stayed the same and V went down. Okay, so now we're ready to try to draw this wave in the medium here. Okay, so we want to do basically two things. We want the amplitude to be slightly less, so here's the rest position line, and we want the wavelength to be smaller. So we want the waves to be much or closer together. How much closer we don't know. So I'm going to try to do this so it's going to be shorter. Try to keep it uniform. That's not too bad so far. Now it's getting awful. All right. So I'm trying to keep the same amplitude, the same wavelength. All right. So that's not the best. I'm sure you can do better than me. Now the question is, what happens when it leaves? Well, when it leaves, all right, most of the energy is transmitted, but some will be reflected. So the amplitude actually get a little bit smaller. Frequency isn't going to change. Speed, well, we're entering a new medium. We're entering the same medium which we started, so it's actually going to go back to the original speed. And therefore, the wavelength will increase back to the original wavelength. So what I'd have to draw is the same wavelength as before, but just slightly smaller in amplitude. All right, I'm not really measuring this length compared to this length. It looks okay. So that's the idea. Okay, so come in with any questions. I believe there is a problem about this on the homework sheet, and we'll talk about that later.